This is the beginning of the next unit, so this will not be on quizzes or tests coming up shortly. You do have a quiz tomorrow on section 5.2 and 5.3, and then the test will be on Thursday. So this won't be on either the quiz or the test that we have this week. We're going to look at what are called Riemann sums. I know it looks like in English it should be pronounced Riemann, but it's German. And so in German, when you have two vowels next to each other, it's the second one that says its name. In English, it's the opposite way. And the double N makes it, instead of man, makes it mon. Anyway, thus endeth the language lesson for today. So if an object has a constant velocity of 16 feet per second, what is its change in position from time t is equal to 0 to t is equal to 6 seconds? Well, it's traveling at 16 feet per second, and the amount of time that it did that is 6 seconds. That's 96 feet. That's a pretty basic concept that you learned in junior high. Rate times time gives you distance. So in most cases, though, the rate of change, and velocity is one example of a rate of change, but it's not the only one by any stretch of the imagination. If that is changing, it's not constant. Rate of change is rarely constant. One way to estimate the change is to divide the time into subintervals and assume a constant rate of change on each subinterval. So let's take a look at this one. We've divided the time from 0 seconds to 6 seconds into 1 second subintervals. By the way, on the AP exam, they almost never do even width subintervals, which is why you have a worksheet tonight, because your book does them all even, and I'm like, that's almost never the way it is on the AP exam. So for a left approximation, what we're going to do is we're going to look at this very first subinterval, and we're going to go, okay, so on that subinterval from 0 to 1, if I want a left approximation, I'm going to take the left velocity and assume that that's how fast that's going for that whole second. So that's going to be 0 times 1. Plus, on the next subinterval, again, using the left hand, we'll assume that it's traveling at 8 feet per second, times, again, that'll be 1 second. And I make sure that I multiply every time, because they're not always going to be equal width. On the next subinterval, for that next second, we're going to assume that it's traveling 15 feet per second, then 21 feet per second, then 26 feet per second for 1 second, and then 30 feet per second for the last second. Occasionally students get confused. They're like, why don't we ever use that far right number? Because it's a left approximation. We're never going to use that very last one in a left approximation. So let's see, 56, 77, 85. Is this 100? Three, 44, or is it 80? Oh man, it's 100? Okay, thank you. So the left approximation is that it's 100 feet. The right approximation, we're going to assume that it's traveling 8 feet per second for that first second, and then 15 feet per second for the next second, 21 for the next, 26 for the next, 30 for the next, and 33 for the last. So that's going to be 133 feet. Now, we can also do what's called a midpoint approximation. What we do in a midpoint approximation is we divide this into subintervals, find the midpoint of the subinterval, and then use that as our constant rate of change. So we would have to have wider subintervals in this case. We would only have 3 subintervals. So on the time from 0 to 2, we'll assume that it's traveling 8 feet per second for those 2 seconds. And then on the next time interval, we'll assume that it's traveling 21 feet per second for those 2 seconds. And on the last one, 30 feet per second for those 2. This comes out to be 118 feet. That frequently happens that a midpoint is between the two. Now, under what conditions will that happen? Well, if the velocity is always increasing or always decreasing, the midpoint approximation tends to come out to be in between those two, in between the left and the right approximation. All right, more generally, here's what a Riemann sum is. We'll consider the function y equals f of x from x equals a to x equals b. I just have drawn a squiggle, basically. A Riemann sum is found by partitioning the interval from a to b into subintervals, selecting an x value in each subinterval, and evaluating the function at each selected x value, then multiplying each function value by the width of the subinterval. So what we're talking about is this. I'm going to divide the distance from A to B into, I'm going to do it into 3 subintervals just to show you. So I'm going to divide it here. And the thing about this is nowhere did it say these had to be even width subintervals, did they? They also didn't say where I should figure out what f of x is. I can use any point I want in that subinterval. So I'm going to go right here. And I'm going to call that x sub 1. And this height is going to be f of x sub 1. And what we're actually doing, since we're multiplying this height times this width, we're finding the area of this rectangle. And you notice that there's a little bit of the curve that's above the rectangle and a little bit that's below. But they're similar in size. Well, what if I picked the lowest point? Well, if I pick the lowest point, then I'm going to miss some. And on this one, I'm going to pick the highest point, just to be obnoxious. So this is f of x sub 3. So the Riemann sum is the summation as I goes from 1 to n of f of x sub I times delta x sub I, where n is the number of subintervals. In this case, it would have been 3. X sub I is the ith value, ith x value. So again, I picked 3 random x values, 1 in each of the subintervals. And delta x sub I is the width of the ith subinterval. So I have the width of the first interval, the width of the second, the width of the third. So if f of x is the rate of change in a function, capital F of x, the Riemann sum estimates the change in capital F of x from x equals a to x equals b. That is capital F of b minus capital F of a. This is an enormous, big idea. If we do a Riemann sum, and we did it with velocity. Velocity is the rate of change in distance. And when we did the Riemann sum, we got an approximation for the change in the distance, or change in the position. It doesn't have to be velocity and position. It could be any kind of a rate of change. For example, if we were doing how many rooms someone could is painting per day, right, and did a Riemann sum on that, we would find how many rooms they painted approximately. So we talked about this briefly, but if a function is strictly increasing, then a left Riemann sum is less than the true value. So if you have a function that's strictly increasing, say you have something that looks like this, when you do your Riemann sum, doesn't matter how many subintervals you divide it into. I'm just going to divide it into 2. Doesn't matter where you evaluate. Hang on a second. If I'm doing the left-hand evaluation, I'm missing some of that, right? I've got this stuff that is above my rectangles that I'm missing. And a right Riemann sum is greater than the true value. One other thing, if a function is concave up, then a midpoint Riemann sum is less than the true value, and if the function is concave down, then a midpoint Riemann sum will be greater than the true value. And that's because if something is concave down, let's do something like this. If that's concave down, if we choose the midpoint as my evaluation, see how we miss a little bit, but we overestimated by quite a lot on the two sides? I find that if I'm asked things like that and I don't remember the rule, a quick sketch is enough for me to go, oh, yeah. And you don't even have to do it into multiple subdivisions. Just draw one. Do it as if it's all one subdivision. All right, let's look at part of an AP problem, or a couple of AP problems. Oh, actually, we're not looking at number 4. I just didn't cut that part out. This was the 2007 AP Calculus AB free response questions. We're going to look at number 5. And we're doing good on time, so we're gonna do all of it, or quite a bit of it. All right, so we have this table of values, and it says the volume of a spherical hot air balloon expands as the air inside is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of time t, where time is measured in minutes. So we have the rate of change in r prime of t. The table above gives selected values of the rate of change, r prime of t, of the radius of the balloon over the time interval from 0 to 12. Also tells us that the radius of the balloon is 30 feet when t is equal to 5. And it gives us a formula for the volume of a sphere. It gives us all kinds of information. It also tells us that the graph of r is concave down. That's going to become important to us in a little bit. All right, so first of all, estimate the radius of the balloon when t equals 5.4 using a tangent line approximation at t equals 5. Is your estimate greater than or less than the true value, and give a reason for your answer. You guys have plenty of room to write this underneath. I'm going to block off B, C, and D for the moment and do it there. All right, so we want the tangent line approximation for the radius at t is equal to 5. All right, well, we need a point and we need a slope. The slope is the derivative. The derivative at 5 is 2. So that's our slope. We need a point also, and they give us that right here. The radius of the balloon is 30 when t is equal to 5. So using a tangent line approximation, I'm going to say y is equal to 30 plus 2 times x minus 5. They gave us all the things that we needed. You just have to parse that they gave them all to you, because they gave you a lot of information on this. So the radius is approximately equal to 30 plus 2 times 5.4 minus 5, which is 30 plus 0.8 is 30.8 feet. Is your value greater than or less than the true value? Well, it tells us that r is concave down. If r is concave down, we draw a tangent line anywhere. What do you notice about the tangent line? Is it above or below the graph? It's above the graph. So this is our tangent line, and this is y is equal to the radius. So this tangent line is always going to be above because this is concave down. So is your estimate greater than? Our estimate is greater than the true value. And I'm going to say the true value of r, because r is concave down, So the tangent line lies above the graph of R. Okay, so that's how tangent lines will get used. They'll ask you to write the equation of a tangent line, then they'll ask you to estimate something using the tangent line approximation. That happens pretty regularly on the AP exam. All right, let me get rid of this stuff. We'll go to part B. Find the rate of change of the volume of the balloon with respect to time when t is equal to 5. Okay. That's old stuff also. We know that the volume, because they very nicely gave us the equation, is 4/3 pi times the radius cubed. So the rate of change of the volume with respect to time, that's dv dt. So it's going to be 4/3 pi times 3 r squared times dr dt. The 3's happily cancel. And we know that dr dt at 5 is 2. This is 4 pi times 2 squared. Drop your pencil and walk away from this problem. Don't calculate that. Yes, I know, you can all do it in your head in seconds. Don't do it. It's a trap. The only thing that can happen at this point, if you do further simplification, is that you lose the point you got for writing this down. You can't get any more points. You can only get less points. So why would you do it? Now, the last part is, it says indicate units of measure. So that's dv dt. This was in feet, so that's cubic feet per minute. You should always be putting the units in, but if they specifically say put units, you will lose points if you don't write them. All right, so again, that's old stuff. Let's look at part C, which is some new stuff. Use a right Riemann sum with the 5 intervals indicated by the data in the table to estimate this thing. And you're like, I don't know what that thing is. It's okay. It just said use a right Riemann sum, and it's going to estimate whatever that thing is. We'll talk more about what that thing is later. But at this point, you don't need to know. You just said do a right Riemann sum. And we learned how to do that today. So we're going to do a right Riemann sum. So I'm going to say this thing, and I'm just going to copy it down. And it said it's an estimate, so I know it's going to be approximately. So I'm going to divide this into the subintervals. And it says use a right Riemann sum. So, okay. So I'm going to use 4 over the first 2 minutes. So it's 4.0 times 2. Plus, on the next interval, that's going to be 2.0 times 3. Plus, on the next subinterval, I use 1.2 for those 2 minutes. Plus, I'm going to use 0.6 for those 4 minutes. Plus 0.5 for that last minute. See how the time intervals aren't all the same? That's how AP asked them. says using correct units, explain the meaning of this thing in terms of the radius of the balloon. By the way, again, this is a free response question on the AP exam. Do not, under any circumstances, take the time to figure out what this is. You can't get any more points. You can only get less. There's no reason to risk that. Well, if I'm talking about units, I'm multiplying feet per minute times minutes. So this must be feet. And just a moment ago, we said that Riemann sum estimates the change in the original function. So this symbol gives the change in the radius measured in feet. It said use units. From time t is equal to 0 minutes to t is equal to 12 minutes. And then it asks in part D, is your approximation in part C greater than or less than? Well, what that symbol does is it actually gives the true value. We'll talk about how all that works in this next unit, but it says, is your approximation less than or greater than? Well, this function certainly looks like the rate of change is always decreasing, right? How do we know for sure that it is? Well, since R is concave down, that was given information, by definition, when is a function concave down? You got to know this one, guys. This needs to be at your fingertips.
Minimum and maximum? The other one?
The other one.
Well, it's either concave up or concave down.
What is the definition of concave down? The derivative is decreasing. That's the definition of concave down. R prime is decreasing. And if we have a decreasing function and we apply a right Riemann sum, are we going to overestimate or underestimate? Look at the picture. Are we getting too much area or too little?
Too much.
We're getting, the Riemann sum is this part.
Oh, too little.
Yeah. So a right Riemann sum underestimates. By the way, Riemann is always capitalized because it's a person's name. Georg Riemann underestimates. All right. You guys have a great day.